Today we are going to look at power signals. Okay, so power signals as vectors in complex vector space. So our discussion from yesterday is how to treat signals as vectors, and we saw real valued signals and complex valued signals, but the complex valued signal that we considered yesterday was energy signal. Okay, but now we are going to extend this further to include power signals, and here we will especially focus on periodic signal. Okay, power, though I am saying power signal, one class of power signal are periodic signals. Now in the case of periodic signal, if you calculate energy, that is going to be infinite. Okay, because all periodic signals or power signal extend from minus infinity to plus infinity. So if you find the energy inside the signal, it is going to be infinite, but power is going to be finite, as we have seen earlier in the classification of signals. So the inner product needs some modification. If you take the inner product in the present form, that is not going to be very useful. Okay, so we are going to modify the inner product definition. So let x1 of t and x2 of t be to power signal. If let x1 of t and x2 of t be two power signals, then their inner product could be defined as inner product of x1 and x2 could be defined as so how we are going to modify, just like instead of the expression for energy, we will use the expression for power. So if you remember the expression for energy earlier, so let me also say that this is periodic power signals. So then the expression for power was given as 1 by t integral over one period. So I am going to put it like this. We could start anywhere, either 0 to t, or we could start from some t0 to t0 plus t. Any of this is okay. Then first function in the same form, then multiply it with the second function by taking the conjugate of it. So this dt. So only difference is the integration limit is from it is over a finite period, not from minus infinity to plus infinity, though the signals are defined from minus infinity to plus infinity. So then their inner product could be defined as so if you look at the definition of the inner product for energy signals, we had say x of t, y of t, we defined it as from t going from minus infinity to plus infinity, first function into conjugate, so here we have taken x of t into y star of t dt. So that was our definition earlier, where x and y are energy signal, where x of t and y of t are energy signal. But now x1 of t and x2 of t, they are not energy signals, they are power signals. So we are modifying. So this is the new definition of the inner product when we have to use this definition in the case of power signals. So this is basically a way of evaluating the power, and we know that power is finite for power signal. and energy is going to be infinite. So that is why we are doing this. So with this definition, so this is yesterday, so I will write it as whereas. So using this present definition, we can talk about all the things that we did earlier. So we can talk about orthogonal set. So now we are going to consider orthogonal set of power signals. So Fourier series will come as an example to this. Okay, it is not just Fourier series. It is, you can apply to any power signal. Sines and cosines are signals which are power signals. So that is why I said that they will come under this category. So orthogonal set of power signals. So let G1 of t, G2 of t, etc. Up to Gn of t form a set of orthogonal power signal. Okay. So to approximate, again the problem is the same. So to approximate a given signal, say f of t in terms of this set of signals as fa of t is equal to sigma ci, I goes from 1 to n. Okay, so let's take capital N. So there are n number of signals in the set, ci gi of t. So this is the expansion we are looking for. Almost everything is the same, so I can maybe skip this derivation. There is no need to again derive the same thing, because we have seen already the full derivation yesterday. So but I want to emphasize that this derivation as well as this concept is very central to signal sum system. So we have a signal f of t, okay, which is in general a complex signal, and that signal we want to express it in terms of this set of orthogonal functions or orthogonal signals in the set. They form a property. The power that is like if you the orthogonal signals, okay, these power signals has the following property. So like yesterday we said, if you take any of this, say gi of t and gj of t, then what is going to happen is that we will get 0 if I is not equal to j. That's the definition of orthogonality. Okay, when you take two functions from the set, if they are different functions, when you take the inner product, you will get 0. But if you take the same function, what is going to happen is that we will get the power of that signal. So let me call it as pi if I is equal to j. So this you can express using a simplified notation called Kronecker delta notation. So the same thing, whatever I have expressed in bracket, that will be written as delta ij pi. Okay, so this is the definition of the orthogonal set. Okay, so only difference here is that the way we define the inner product, that is different, otherwise everything is same. And therefore we can use this property and find the mean square error just like yesterday, and then minimize the mean square error with respect to the constant. And so I will leave it as a homework. So homework, show that the best approximation is when Ci is equal to f of t inner product with the gi of t divided by gi of t inner product with itself. Okay, there is only minor differences. Okay, instead of energy these are power, but that hardly matters in the derivation. Okay, so the derivation steps are exactly the same for the power signal also. Okay, so now let us consider practical cases of orthogonal set. So let us look at the following set. So I'm directly going into what is called as trigonometric Fourier series. So in trigonometric Fourier series, the set of orthogonal functions are is given us. So we have a set here. So that contains, the first entry is a constant, that is the first function, and constant is also a power signal because its energy is infinite, and the constant value is 1. The second entry is say cos some omega 0t. Next entry is cos 2 omega 0t, then cos 3 omega 0t, and it goes on. And there are infinite number of terms in the set. So capital N in this case is infinity. Okay, and similarly you have sin omega 0t, then sin 2 omega 0t, sin 3 omega 0t, and this also goes up to infinity. Okay, so this is the set of that we are all of them are power signals. Okay, because they are periodic as well as power signals. You can concisely notate this like this, 1 and then cos n omega 0t and then sin n omega 0t, where n goes like 1, 2, 3 up to infinity. So this way you can represent this orthogonal set. So we are going to now apply this theory that we have derived. Now we are looking at periodic signals. So now the claim is like this. So our claim is this: any periodic signal, okay, with period t, and t can be also written as 2 pi by omega naught, Omega naught is also called the fundamental frequency. Any periodic signal with period t equal to 2 pi by omega naught can be approximated using the trigonometric Fourier series orthogonal set. Trigonometric Fourier series ortho. This is our claim. Okay. And the best approximation, is when so we have to define the constant. Okay, so let us define the constant. The best approximation. So any periodic signal, say let's say name it as f of t with period t equal to 2 pi by omega naught, can be approximated using the trigonometric Fourier series orthogonal set. The best approximation for the function. So I am going to write that approximation. Fa of t is, so usually the constants that we will use is a naught into the first function in the set, which was 1, plus sigma I, or let's use the letter n now. N goes from 1 to infinity, a n cos n omega 0 t plus n goes from 1 to infinity, bn sin n omega 0 t. So this is exactly the similar thing like earlier we said, fa of t is equal to sigma ci gi of t. This is exactly the same. I goes from 1 to n. That is what we earlier said. So here gi's are basically the functions in the set. One of them is 1 constant. Second one is cos n omega 0 t, where n can take values from 1 to infinity. So there is an infinite number of cosine functions. And then another set of functions in the set is sine functions, so with varying frequency, which are like harmonics of the fundamental frequency. Omega 0 is the fundamental frequency, that is cos omega 0 t and sin omega 0 t. These are fundamental frequencies, and when you multiply that with a n, a positive integer, you get a harmonic. 2 omega naught is called the second harmonic. Okay. Any questions so far? Is it all clear? Can you relate whatever theory that we learned with this particular case? I would like you to interact.
Sir.
Yeah.
So what if in case of any random signal, can it be approximated near to standard signals?
Random signal, the problem with the random signal is that we can't write down any expression. That's the problem. If we could find out the expression for f of t, which is a random signal, then we can do this also. We can do this. But the problem is that f of t don't have any specific expression. Whereas periodic signal, we can write down they are deterministic signals, so we can write down the expression. So any function, whether it is periodic or non-periodic, but right now we are focusing on periodic signal. whose expression can be written down, we can apply this method. We need to know f of t, then only we can do this method, because to find out the constants we require the expression for f of t. Is that clear?
Yes, sir.
Okay. Okay, so only thing that we did is that we have fixed the form of gi of t here. Okay, so earlier I said the orthogonal set is given by g1 g2 up to gn. Now we are specifically telling what is that gi, g1 g2 g3. Okay, so for example you can say g1 is 1, g2 is sin omega or cos omega 0 t, and g3 is cos omega 0 t, and then g4 is cos 2 omega 0 t, and g5 is sin 2 omega 0 t. Like that it goes on. So we are specifying what the functions are. So, and depending upon what functions form the orthogonal set, we can have different kinds of approximation. So is that clear to you?
Yes, sir.
Okay.
Sir.
Yeah.
So, but about the sine and cos components of the signal. So, at the same time, things are both components are not possible.
Okay, so I am yet to show you the orthogonality condition. Okay, so first let us check for orthogonality condition. So I think that will clear your doubt. Check for orthogonality. So what we need to check, as I told you earlier, if they are power signal, x1 or let's say gi of t, if I take inner product with the gj of t, what will I get? I will get delta ij pi. So let us check whether that is the case. That means whenever g and I and j are different, we should get 0. So then only we can say any two function you pick from the set, their inner product should be 0. So let us start. Let us start with number 1. I can take 1 and cos n omega 0 t. These are two functions in the set. So these are different functions. So I should get 0. So I have to check whether this is 0. So LHS is what? This is first function into. So 1 by t is there now. These are power signals. So 1 by t. Let me take integration from 0 to t. Then conjugate of the seconds. These are real functions. So cos n omega 0 t dt. This is, if this is 0, then 1 and cos n omega 0 t are 0. So what is this? So this is equal to 1 by t. Integral of cos is what? Anybody? Integral of cos is sin n omega 0 t divided by n omega 0, right?
Sir.
And the limit is from 0 to t. That is equal to 1 by t. Put the upper limit. Now what is t? 2 pi by omega 0. So we can substitute that for the upper limit, n omega 0 into 2 pi by omega 0. I put small t equal to capital T. Okay. Instead of putting capital T, I put 2 pi by omega naught, because t is equal to 2 pi by omega naught minus sin 0. Okay. So there is again some constant here, n omega naught. Now look at this. This omega naught cancel. Sin n 2 pi is what? Sin n 2 pi is what?
0.
0. And sin 0 is also 0. So it's 0 minus 0, and therefore it is equal to 0. So we have shown that for any n value, 1 and cos n omega 0 t are orthogonal. It is proved automatically for n equal to 1, 2, 3 up to infinity. Cos omega 0 t and 1, cos 2 omega 0 t and 1, all of these are orthogonal signal because it doesn't depend on n. It is 0. Second thing we need to show is 1 and sin n omega 0 t. So we have to check whether this is 0. So again LHS is 1 by t integral 0 to t first function which is 1 into second function conjugate, because these are real function, n omega 0 t dt. Same approach. Now if I want, I can write t, this t also as 2 pi by omega naught, so I will get omega naught by 2 pi. Now integral of sine is what? Integral of sine
minus cos.
Minus. Okay, so I am taking the minus sign outside. So this is cos n omega 0 t divided by n omega naught. Okay, and the limit is from 0 to say 2 pi by omega naught. 0 to t. Okay, t is basically 2 pi by omega. Now I can cancel this and this. So I can write it as minus 1 by 2n pi, that is a constant, and in bracket I have cos n omega naught into 2 pi by omega naught minus cos 0. Again omega naught cancel. Cos 2n pi is what? Cos n 2 pi or 2n pi.
So minus 1 to the power n.
No. 2 pi. It's multiple of 2 pi, not multiple of pi. N is a positive integer multiplying 2 pi.
So 1.
1. Correct. And cos 0 is what?
So 1.
1. So this is 1 minus 1 in the bracket, which is also 0. Okay. If I want, I can say 1 minus 1, which is equal to 0. So that is also proving it. Now what is left to show? What is left to show is we need to now show the inner product between cos n omega 0 t and sin n omega 0 t. This we have not shown. All the other cases we have shown. So in order to show this, so this is a case where n could be any value, but if I take 1 here also it will be 1. So these are the case where in both harmonics are same, but one is sine, the other is cos. A part B of this proof is where we have to take n and here n and there m. Okay, so that is also needed to be shown. Or okay, let us show this one. What is going to happen? So this is equal to in 1 by t integral 0 to t first function, that is cos n omega 0 t, conjugate of the second function. There is nothing to take conjugate because this is positive valued function. So that is sin n omega 0 t dt. Again I can write this as omega naught by 2 pi integral 0 to 2 pi by omega naught. Then what can I do with cos theta sin theta? I can use the trigonometric relationship, probably you know. Can you tell me? If I multiply this with 2, then I have 2 cos theta sin theta, or 2 sin theta cos theta, and divide by 2. So I will do that and write it as, so I will have an extra factor of 2, and then I will write this as sin 2n omega 0 t dt. Is that right? You agree?
Yes, sir.
Yeah. So omega 0 divided by 4 pi, and let's integrate now. What is the integral of sine? Again minus cos 2n omega naught t with the limit 0 to 2 pi by omega naught, and then it is also divided by 2n omega naught. Okay, so omega naught cancel. What we are going to get is minus, if I take all this constant term, 1 by 8n pi, and inside bracket I will have the upper limit, if I put, that is cos 2n omega 0 into 2 pi by omega naught minus cos 0. Again omega naught cancel. It is cos n 4 pi, and the value is
1.
So again it is 1 minus 1, so this is also 0. Now the last case that we need to show for orthogonality is when sine or cos have a different m. Okay, so that is the last. Cos n omega 0 t and sine m omega 0 t. So this case we have not seen. Earlier case both were same. So this is a different case. So for example, cos omega 0 t and sine 2 omega 0 t, are they orthogonal? Okay. So that is also 1 by t integral 0 to t plus function cos n omega 0 t into conjugate of the second, which is sine m omega 0 t dt. Now can you suggest how to proceed? You see sin a cos b form or cos a sin b form. So what we can do? Anybody? Integral.
Dividing by 2.
No. These are different values, right? This is not theta, right? It's not cos theta sin theta. This is theta 1 and theta 2. They are different. So we cannot apply the earlier formula. They are different values. So what we should do? Again we can multiply and divide with 2. Probably you must know the trigonometric expansion for 2 sin a cos b. 2 sin a cos b is what? Sin
A plus b plus sin a minus
m plus n omega 0 t, then plus sin m minus n omega 0 t, right? Do you agree?
Yes, sir.
Yeah. So if I do this sum, I will get 2 sin m omega 0 t and cos n omega 0 t. Okay. So that we can integrate now. That is omega 0 by 4 pi into, I will do it as 2 integrals. So it is given that m not equal to n. If m is equal to n, it fall back into the previous case. So here we are considering a case where they are different. Okay, so if they are different, the difference and the sum m plus n is also integer. Say 1 and 2 or 3 and 4, when you add them up, 1 and 2 when you add up you get 3. 3 and 4 you add up you get 7. So m plus n is an integer. and m minus n is also integer. 1 and 2 you can get either minus 1 or plus 1. Okay, so it will all be integers. The difference and the sum will be integer. So let us integrate the first function. Integral of sine is minus cos. So minus, let me take it outside. So cos m plus n omega 0 t divided by m plus n omega 0. So that with the limit 0 to 2 pi by omega naught. Then plus, similarly we will have cos m minus n omega 0 t divided by m minus n omega 0. This also has same limit. Okay, so if you put the upper limit, what will it become? It is an integer multiple of 2 pi. Any integer multiple of 2 pi you are going to get 1, and the lower limit is also 1. So 1 minus 1, 1 minus 1. Agree?
Yes, sir.
Yeah, so this is also 0. Okay, so I have not written it down explicitly, but because we have already seen that. So these are the only cases where the functions can be different. So if you pick, there are infinite number of functions, but if you pick any two functions which are different, it will fall into any of these cases. Okay, and in all the cases the inner product is 0. So they form an orthogonal set. Now what is remaining is to show is like if they are same. If they are same, I said we will get the power of the signal. Okay, so let us do that also. Power of signals in the trigonometric Fourier series orthogonal set. So the first one is 1 inner product with 1. So that is very easy. 1 by t integral from 0 to t, first function into integral conjugate of the second dt. That is 1 by t. Integral of dt is t. So that is correct?
Yes, sir.
Yeah. Number 2. So let us now consider cos n omega 0 t inner product with cos n omega 0 t. So 1 by t integral 0 to t, first function into conjugate of the second function, which is also same. So I can write it as cos square. Agree?
Yes, sir.
Yeah. So now I can use trigonometric relationship. So this is omega 0 by 2 pi. Integral is also from 0 to 2 pi by omega naught. What is the trigonometric identity connecting cos square n omega 0 t? It is 1 plus
2.
cos 2n omega 0 t by 2, right?
Sir.
Yeah. So dt. So that is omega 0 by 2 pi. Okay, let's write it as 4 pi because there is a 2 coming from here. And then I have two integrations. The first one is basically 0 to 2 pi by omega naught dt. and the second one is integral 0 to 2 pi by omega naught cos 2 n omega naught dt. Okay, so the first part is easy. Omega naught by 2 pi, you integrate, you get t, and then so it will be basically 2 pi by omega naught. What about the second part from the experience that you had? Okay, I will write one more step. So integral of course is sine 2 n omega 0 t divided by 2n omega 0. Is there any minus sign? No. So 0 to 2 pi by omega naught. So this is what we will get. Now if you look at the upper limit, when you put t equal to 2 pi by omega naught cancel, again it is 4n pi or n 4 pi. Upper limit is 0, lower limit is 0. So this quantity is 0. But this quantity will survive. So we can write, cancel the 2 pi. I have left 1, 2 here. There is a 2 here. This is 4 pi. Okay. This is omega naught by 4 pi. So 2 pi cancels, and then you will get what? 1 by yes, half. So that is the power of the cosine signal. Now the last part is the energy of, so all the cosine irrespective of the frequency, whichever harmonic, whatever is the value of n, we will get the power equal to half. Now similarly I can do sine n omega 0 t inner product with itself. So that will be 1 by t integral 0 to t sine square n omega 0 t dt. Again I use the trigonometric expansion, and I will write it as 0 to 2 pi by omega naught 1 minus cos 2n omega naught t dt. And what should be the answer? Can you tell now? Without doing, you don't need to do anything. You should be able to tell the answer directly from the previous result. Except for a sign change in the second term, everything is same. But the second term is 0, so sign should not affect the result.
Yes, sir. It will be half.
It will also be half. Okay, so now we got everything that we require. We got the energy. We got we have proven that they form an orthogonal set. Okay. So now coming back to our question, what was our problem? Our problem was to expand a given function in terms of this orthogonal set of function. We just showed that they form an orthogonal set. We have checked the orthogonality. So now let us evaluate these constants using the formula that we derived earlier. What is A0? What is AN? What is BN? Okay. So let me just do that. Okay. So let me say evaluating the constants A0, AN and BN. These are the trigonometric Fourier series coefficients. Now, what is A0? Can you tell the definition? What is A0? based on the theory we learned. Go back to the theory. A naught is given by what? Any constant is given by this formula. Okay, this is the formula for best approximation. So this is a very, very important formula. Only the inner product definition varies, but the formula is same, whether it is single function, whether it is real valued function, complex valued functions, power signal, energy signal, it is all giving you same formula. Even we can use it for ordinary vectors. Only thing is inner product has to be changed to dot product. That's the only difference. So this is a very powerful result which we can make use for any orthogonal set. So now tell me, based on that formula, what is A naught? A naught is f of t inner product with
g of t.
Which g of t I should take in the trigonometric series? You see, our trigonometric Fourier series set is this: 1 cos n omega 0 t sin n omega 0 t. So I associated one constant with each of this function. I will show you again. After that you have to tell me. You look at, I have associated the expansion coefficient with each function. So A0 is associated with which function?
1.
An is associated with which function?
Cosine omega t.
So you note down this, and then knowing that you can apply to the formula. So f of t inner product with what? What should I write here?
1.
Divided by what? 1 inner product.
1. Yes, sir.
Yeah. Which we have already found out. 1 inner product 1 is obtained as 1, right?
Sir.
Yeah. So this is equal to, so the denominator I am going to write it as 1 by 1 into, or maybe I will write like this. Let's apply the definition. 1 by t integral 0 to t f of t dt. F of t multiplied with conjugate of 1, but that is just 1 only, and divided by 1. Agree?
Yes, sir.
Yeah. So this is 1 by t integral 0 to t f of t dt. Have you seen this formula in mathematics? Did you study Fourier series earlier? Yes or no? Did you study Fourier series earlier?
So not earlier.
Not earlier. Okay. So then this is the formula to evaluate A naught. And then An, can you tell me the procedure? Just like this. An inner product of f of t comma
Cosine omega naught t.
Correct. Cos n omega naught t divided by what?
Cosine omega naught t.
Cos n omega naught t with the cos n
Cosine
omega naught t, which we have already done. How much we got? Half, right?
Yes, sir.
We got half. So integral 1 by t integral 0 to t first function into conjugate of the second cos omega 0 t dt divided by half. This is equal to 2 by t integral 0 to t f of t cos n. Clear? Okay, now the last one. We have one more set of constants. This a n is for all values of n. We have derived it just in a generic way. Similarly, we can derive in a generic way for bn also. So this is f of t not product with sin n omega 0 t divided by sin n omega 0 t sin n omega 0 t is equal to 1 by t integral 0 to t f of t sin n omega 0 t dt divided by half again. So this is 2 by t integral 0 to t. Now it is not necessary that we should start from 0. You could start from minus t by 2 to plus t by 2 also. Okay, anywhere you start, you have to integrate over a period of t. So that you have to keep in mind. F of t sin n omega 0 t. So these are the Fourier series expansion constants. So these are also called as Fourier series expansion. Trigonometric Fourier series expansion coefficient. Trigonometric Fourier series coefficients.
Sir.
Yes.
Sir, yes, sir. We have seen earlier this one, Fourier series.
Yeah. That's what I thought. So we have now derived those formula. How does that formula come? We have derived by using a vector concept. Okay. So that's why I said this is a very powerful concept, and it is not just for Fourier series. You can take any other. There are, in large number of series that are available, like Legendre polynomials or Hermite polynomial. Those are defined for different domains. Okay, for say maybe t varying from -1 to +1. Certain cases are like that, or Zernike polynomial. So there are lots of orthogonal function set we can think about. Okay, for different range, maybe from 0 to 1. 0 to infinity, minus infinity to plus infinity, there are infinity. We will see one more set, that is exponential Fourier series. Okay, so maybe we can directly go to that after a break.